Okay, our class today will be on the electrostatic potential energy. Now, potential energy reflects the work that you have to do to move a charge around in an electric field. Let's imagine we start with a small charge q here, a distance r or d away from charge minus q, and we move it away to infinity. Now, the positive charge, because of the electric force on it, will need to be pushed. And we're finding the work done by this push force. So that's the force diagram for this charge. Now directly underneath that, we can sketch a graph. If we move this at constant speed, these two forces will be balanced with each other. And we know that the electric force obeys an inverse square law. Excuse me. So the push force will as well. So we see we have a force versus distance graph that is an inverse square, and consequently if we want to find the work, we're going to need to integrate. So you can just add that to the graph here. Now we'll remember that the force of electricity, as we said, is given by an inverse square law, Coulomb's law, so that if we want to find the work done, we're going to have to integrate. So let's set up that integral. So we're going to go from a distance d or r all the way out to infinity, and the work done is just going to be the force times a small bit of displacement. So that's kqq over r squared, where these are assumed to be positive, so we'll take absolute value. Now the kqq is a constant, so that'll come out. And then this is going to be r to the minus 2 dr. Now that integral is r to the minus 1 over minus 1, and the limits are d to infinity, That is, in turn, minus 1 over r from d to infinity. We get rid of the minus by reversing the limits, so it's 1 over r from infinity to d, which is 1 over d minus 1 over infinity, and 1 over infinity is 0. So we get for this work kqq over d, or if you like, kqq over r. So there's our integral, and we see that the amount of work done in this case in separating those two charges is a positive number, kqq over r. Now, if we do work and move this charge out to infinity, we know that at infinity there's no energy, there's no potential energy. So if we've done work and ended up with 0, our initial energy must have been negative. So for unlike charges, you have to have a negative potential energy. If the charges are like charges, then it's going to take work to actually push them together. So starting at 0, you do work. Obviously, you're going to end up with something positive. So potential energy has to be negative for unlike charges and positive for like charges. So the answer is going to be positive or negative, and you'll have to either remember to put that in, or you can drop the absolute value and actually use the plus or minus signs of the two charges to get the correct SIGN for the potential energy. So you see, if you have like charges, plus, plus, minus, minus, it'll end up positive. If you have unlike charges, it will inevitably end up negative. So here, no absolute value. Unlike electric force and field, where we just put in the magnitude, here we're actually going to put in the SIGN of the charge as well. So some quick examples here, calculations of potential energy. So these are just kqq over r. So for this first example here, we have an electron and a proton. There's the separation distance. So it'll be k. We remember that an electron is -1 fundamental charge, and a proton is positive 1 fundamental charge. So this is going to end up with negative potential energy. We're not including the units here. For the next case, we got a microcoulomb and 3 microcoulombs. So for this problem, it'll be K. It's a microcoulomb, positive, and then it's 3 microcoulombs, positive, and then the separation distance is a ½ meter. Now, you can compute these and then compare with the answers that are given here. Now, for this last potential energy, there's going to be several terms. KQQ over R. So first you're going to have 1 coulomb and minus 3 coulombs, and that's separated by 50. So there's the potential energy of those two. Then there's the potential energy of these two. So that's 1 coulomb minus 2 coulombs, again separated by 50. But there's going to be a final term, the potential energy of these two. That's minus 3 and minus 2 coulombs. Those are full coulombs. There's no metric prefix there. And then the distance will be this hypotenuse. This is going to be a 1, 1 root 2. So this distance just works out to be 50 times the square root of 2. So those are the 3 answers to those exercises, and we'll just paste them in here in the right spot. Okay. So you can again compute those, and hopefully those agree with the answers that are provided. All right, so next, another example. Let's here find the amount of work done to separate these charges. So at the beginning, initially, they're in close together. So energy at the beginning plus work equals energy at the end. Energy at the beginning is just going to be the PE. There's definitely some work done because you're pushing on it to separate these charges, which are unlike and therefore attract each other. At the end, you're out at infinity and at rest. So at infinity, KQQ over R, KQQ over infinity will be 0. There's no energy at infinity, and clearly it's at rest, so there's no kinetic energy either. So we start off with some potential energy, PE. We do some work, and at infinity at rest, there's 0 final mechanical energy. So the potential energy is just going to be KQQ over R initial. And so we bring this over to the other side to determine the work. So keeping the minus sign, K is 9 times 10 to the 9. So the two charges, first of all, we've got positive 120 microcoulombs. Then we've got, and I'll have to squeeze it in here because I'm running out of room. Then we've got negative 75 microcoulombs. And so the negative, positive, negative gives an answer that's overall positive. And then we divide by the initial separation distance of 0.03 meters. This works out to 2,700 joules positive of work done to separate those charges. You definitely need to do work because they attract each other, so you have to push them apart. So those are typical work energy problems involving electrostatic potential energy. Now let's talk about the constant companion of electric potential energy, which is voltage, or more formally called electric potential. Now, as we've seen, this is a ratio, right? It's a ratio of energy per charge. And what are we talking about with energy? Well, the energy we've just seen is related to the work done to separate the charges. So if you've got a positive charge and another, say, negative charge, I think this is supposed to be a negative charge, then you have to push them apart. So obviously there's some stored energy here. In a battery, the chemical reactions make one end negative and another end positive. So you can think of this as being, you know, there's been some work done to separate the negative charges from the positive charges, and therefore there's stored energy there. Okay, it seems like we're recording again here. Are we? Yes, we are. Okay, good. So the units of voltage are volts, and a volt is a joule per coulomb. It's an energy per charge. Now notice a voltage divided by a distance, volt per meter. Well, a volt we've just seen is a joule per coulomb, so there's a volt per meter, but a joule is a Newton meter. So a volt per meter ends up being a Newton per coulomb, consequently a unit of electric field. So as we saw already, the electric field, say for parallel plates, is the voltage over the plate separation. So volts per meter is a good unit of electric field. Now, gravitational analogy is helpful. Voltage is like the height of a mountain. Field is like the slope of a mountain. Obviously, force is like the weight, and potential energy, well, that's just like mgh. So with electrostatics, there's a gravitational analogy. Now we can make some graphs here. So for point charges, for a point charge, a single positive point charge, we can visualize the voltage mountain. We know from previous experience that the voltage is an inverse law, and so it's a slope like that, and the electric field would be the slope of that line. Whoops, that's not where we wanted that. We wanted that right about here. There we go. Okay. And in a battery, we saw last time that the electric field is uniform and that the voltage increases nicely with distance. So we'll just squeeze a little graph right on top of our Duracell here. So this will be the negative end, and this is the positive end of the Duracell. So this is the 0 voltage end, and then this is the positive voltage end, so this would be like 1.5 volts for a Duracell. This again is voltage over distance. The voltage increases nice and uniformly with distance. Alright, so let's park that in here. Perfect. You can put that graph on the top of that. So, alright, now knowing the voltage function, we can find the potential energy because we know that voltage is energy per charge, so potential energy should equal charge times voltage. And because work done is the energy change, energy at the beginning plus work equals energy at the end, if the energy is potential energy, and we've just said that's QV, assuming there's no kinetic energy involved, the work done in setting up a charge distribution is just the charge times the voltage difference. Now I make those voltage V's look like script V's just because we're about to have velocities in there as well, say for electron guns. Now, what is the relationship for voltage? Well, we said it's an energy per charge, and potential energy we know is KQ over R. So if you divide by Q, then what you get for voltage is KQ over R. So this is the voltage or electric potential of a point charge Q. K is 9 times 10 to the 9 as always. Q is the charge creating the field. And D or R is the distance to the field point. Now voltage can be positive or negative just like potential energy. Okay? So you've got to remember to insert the sign Q of the point charge. So some simple examples. Let's find the voltage 1.2 meters from this 0.2 microcoulomb charge. Well, that will be KQ over R, so that's 9 times 10 to the 9 Newton meters squared per coulomb squared. We've got 0.2 microcoulombs, and then our distance is 1.2 meters. So coulombs cancel. One of the meters cancel. Newton meter per coulomb is a joule per coulomb is a volt. And it should work out to be 1500. Next example. Let's find, let you look at that for a second. So the answer is given as 1500. Next example. Let's find the total voltage at this point X. So there'll be contributions from both charges. So the total voltage will be the voltage of the 1 coulomb and the voltage of the minus 2 coulomb. So we'll have kq1 over r1 plus kq2 over r2. These aren't vectors, so we could just add the numbers. So q1 is 1 coulomb, and we're 2 meters away from it. q2 is minus 2 coulombs, and we're 1 meter away from it. So the answer should work out to be 13.5 times 10 to the 9, which is giga, or 1.35 times 10 to the 10 volts. Okay, so then what's the potential energy of a small test charge put at that point? Well, if you know the voltage, the total potential energy is just the test charge times the voltage. So it's 0.23 microcoulombs times this negative 13.5 gigavolts. And multiplying, you should work out, first of all, remember giga is 10 to the 9. It should work out to minus 3.1 kilojoules. Okay, a couple more examples. Let's find the potential at a couple of points here and then find the work done to move a charge from a point X to a point Y. Well, we derived a few pages previously that the work done will be the charge times the difference in potential. I suppose we should really start from first principles and say energy at the beginning plus work is energy at the end. The energy is just potential because it begins and ends at rest. Potential is just QV, so when you bring it over to the other side, you get Q times V final minus V initial. Okay, so we're moving from X to Y, so Y is the final point and X is the initial point. And so the potential at the point Y, we're 2 meters away, so that'll be K times minus 2 microcoulombs over 2 meters. The potential at X, we are only 1 meter away. So the little charge Q is 1.2 millicoulombs. That's 1 times 10 to the minus 3 coulombs. So, we were asked to first find the voltage at X and Y. So at X, that would be this term. At Y, that would be that term. Then we subtract them and multiply by the test charge, and you should get the given 10.8 joules of work. A final example for you here now. Let's find the place where the electric potential is 0. So, unlike electric field where there's no vector, for the potential to be 0, it must just be that the two potentials have the opposite polarity. So let's imagine we're a distance x from this one. That means we'll be 2 minus x from this charge. And you can see one's positive, one's negative. It's possible that this will add up to give you nothing. So this is the equation that we now want to solve for x. So we'll bring the negative 1 over to the other side. And then I'll just write it in microcoulomb. And as we did previously, we're going to cancel microcoulombs, which means canceling the 10 to the minus 6, and we'll also cancel out the k. So you get 1 over x is 3 over 2 minus x. Now you cross multiply and solve for x, and you should get x is 0.5 or a half. So this is a slightly different solution from what we had earlier, where we had a vector argument, if we had to have the two vectors being opposite to each other. Here it's just the one's positive and one's negative, and they cancel out. Now this is electrostatics on speed. This is quite a difficult example with lots of different details. So it's a 3-charge system and there's a field point x. So you want to find the force on this charge. You'll have to add a couple of vectors. The answer is given here. The field at x, there'll be 3 field vectors because each of those 3 charges, this one gives a field here, this one gives a field here, this one also has a field at the point x. You'll have to add those 3 field vectors to get the answer to B, which is given here. The energy of the system, well, we did one example like that earlier. There's an energy, an energy, and an energy that need to be added, 3 of them. And the voltage or potential at x, again, you'll have contributions from each charge. Add them together, see if you get this. So your job is to try and work that out. I'm not going to do the answer to this one. We'll go through the solution if you like when I get back. But try to get the answers for those four.